Hello. Yeah, my name's Tane, and I'm going to be talking a bit about how you can optimize your Python program with its garbage collector. It is an introductory talk, so I'll be giving basic usages at the end of the talk, but start with, I guess, the core concepts of this. So, first of all, what is a stack and what is a heap? Well, a stack is a, I guess, part of the computer memory that stores temporary data or, I guess, values for function calls. It follows last in and first out. So basically, the things that get put into the stack go to the top of the stack, whereas the things that get taken out are taken from the top of the stack. The heap, on the other hand, is a region of the memory block that is dynamically allocated during the program execution. So basically, longer lasting things like, I guess, classes or larger objects get put into the heap. The stack itself is not very flexible, and its memory size cannot be, I guess, changed during program execution, whereas the heap can. The reason the stack is better is because it's closer to, I guess, the part of your computer that actually runs these programs, so it can be accessed quicker than the heap, whereas the heap tends to have more space to store stuff in. So, what do they store? Well, I guess I've already said that the stack stores function calls, local variables, and also control flow, while the heap memory stores in Python lists, dictionaries, and user-defined instances. User-defined instances being Python classes and some other things. So an example of the stack and heap allocation are this program calls example, which defines a list into X. The variable X is then stored onto the stack, while the list itself is stored onto the heap, because, well, it's a list, not the label X, which I'll talk about in a moment. Then the function returns X, and when it returns X, it takes X, the variable X, off of the stack. And then, but it doesn't do anything with the list on the heap, because it now has a reference, which is in result. He's gone, so I can't do anything about this, but
Oh, I think there's a button on one of the screens, a mini screen. No, look to your right.
Oh, here?
No, keep looking on the wall.
Oh, there. Gotcha.
oh. Let's say it's on.
Turn it off and turn it on again. Does it work?
Because someone walked off that was like screencasting to the monitor or something?
I think it's at 7 o'clock it kind of turns off and needs to be turned back on again.
Yeah.
And so it's kind of 5 minutes since the talk. We started at 6:55.
Silly.
It is unfortunate, but it's just how Shizzy's have it set up. And
Right. Safety measures.
There's a remote control around somewhere.
Well,
That makes
this
sense,
has
yeah.
like no controls.
Push all the buttons. There's many buttons to push, yes.
It's blue lights on, so it's just the TV that's turned on.
Oh, here we go. Oh, yeah, there we go.
Yeah.
That was the button.
Yay.
Okay. Took a while to find it.
Okay, now that we're back, I explained that the variable x itself is on the stack, whereas the list is on the heap and stays on the heap after the return of the function, whereas x gets taken off. I guess after that, result is put onto the stack and references the list which is on the heap. So I guess how does Python store variables? Well, in C, values are stored as, I guess, generally either memory addresses to where it is in the memory, or it's just stored as values in the variable. Python, on the other hand, creates labels, which reference objects in memory rather than directly storing these values. So what are the attributes of this? I guess a Python object has a type and a value, so, well, I guess that's kind of obvious, but then it also has a reference count, the number of things, I guess, referencing this object. Say back in the program over here, I went result2 is equal to result. That would be referencing the list, which was defined in the function example. So the way to see how many references a variable has, you can use sys.getRefCount, which will print this for you. The main advantage of reference counting in Python is that, well, first of all, multiple names or variables can reference a object in memory, but also when the object's reference count reaches 0, it can, the program can clear that memory because, well, it's no longer used anywhere. This prevents excessive memory usage, which will be shown in one of the demos later. And with larger programs, it does save quite a bit of time. Since objects are, I guess, freed as soon as they reach a reference count of 0, we can predict when the memory will be released, which I guess isn't often relevant since in Python you don't need to think too much about memory management, but it can help. However, this isn't enough to have optimal, I guess, memory management. You first of all have performance overhead. Incrementing and decrementing the reference count adds a small but constant performance cost, which does really stack up if you have larger programs. It's not thread safe. Having, I guess, reference counting can cause issues in multi-threaded programs due to potential race conditions. And the biggest of all concerns, and the one that I'm going to be talking about today, circular references. If two variables reference each other, even after you delete them, each object in memory will still have a reference to the other, meaning that it will never be, I guess, cleared by the Python's reference counting. So here's an example of a circular reference. We have a class node, and A and B are defined as instances of that. We set A as B, and then B as A, and then delete the two. Oh. I forgot to show, I guess, the reference count still being 1 on each, but I do have a demo for this. So basically, even after you delete A and B, they're still in the memory because they're still referencing each other, and the Python's reference counting hasn't deleted this. However, Python has a garbage collector, which will solve this. So What is a garbage collector? Well, a garbage collector is used for automatic memory management. Basically, reclaims memory that is allocated to the program that is no longer used. Some languages that use this are Python, Java, Go, JavaScript, C#, and Ruby. Now, what about the Python garbage collector specifically? Well, the Python garbage collector handles most memory deallocation immediately. The garbage collector provides a safety net that catches circular references and other complex memory issues that reference counting cannot really address. The Python garbage collector always starts with generation 0, the newly created objects, such as local variables. If these either have a reference count, well, no, that's done by the reference count thing, but if these have things like circular references, it clears it out. But if it doesn't, then the object moves on to being a generation 1 object. The generation 1 object is less frequently checked by the garbage collector. And if this has the same issue, then I guess it survives collection and then goes to generation 2. Generation 2, the same thing again. If it has 0 references, then it just gets collected by the garbage collector to free up some of your memory. The generation 2 objects are usually things like global variables, or I had another example written here, which was persistent data structures. And yeah, I think that has helped you understand what garbage collectors are and a bit more about memory. I have a few demos that I want to show today. Actually, I probably could have. Yeah. So this first example is an example of using the garbage collector. It doesn't actually collect anything, but basically this is enabling the garbage collector.
Could you increase the font a little bit,
Oh,
please?
yeah. I actually had an issue with that on my last meetup as well.
That's great.
because
Thank you.
I'm used to tiny text. Is that readable to everyone?
Yeah, a bit more large would be great.
Okay.
One more.
I'm gonna just do this then. Oh no, I can't do that because I'm sure. Yeah. Okay. Yep. Then maybe just do about that much for now. So GC, or the garbage collector, is a Python library which you can just import. It has quite a few things, but the main ones are gc.isEnabled and gc.collect. gc.collect allows you to intervene the program and manually collect the garbage. So you just run that collection rather than having Python do it manually. This is literally just, actually I should probably zoom in for this as well. So we haven't actually allocated any objects in this program, so it says that we've collected 0 objects, but we've enabled it and then manually we've checked whether it's enabled or not, and then we've manually collected it there. The second program here is an example of circular referencing. So we create a little class right here, and then we do what we saw earlier, where we, I guess, reference each variable to the other, or each label. We then get the stats of gen 0 collections right here. I'll run this to show you what it's doing. So yeah, as you can see, the two objects were unreachable. So the garbage collector just, I guess, collected the two objects for us. The third program is, I guess, a example of how manually intervening and manually collecting this garbage can actually help speed up your program by actually quite a significant amount. So this, well, I guess as the name suggests, and as you can see, just appends a lot of data to a Python list. I have two functions, run with GC enabled and run with GC disabled. And the first one, well, it just runs it with the garbage collection enabled. The second one, it's disabled, and we manually collect it after we've called the heavy allocation function. So, and then they both actually print out the time it takes. So if we try running this, you can see that 0.5 seconds is pretty significant for a relatively small program like this. I know that I have allocated lots of stuff to the list, or lots of values to the list, but larger programs do go far beyond what I have done. And especially with companies that do things like microtransactions, you really can't be missing even a single millisecond. So I think this kind of does show some value in actually using the garbage collection library over just letting Python do it all for you. If you look out on the internet, there are many more capabilities of the garbage collector. Just didn't really think I would have the time to go into that stuff this time, but I would recommend looking more into the garbage collector, since it can sometimes be useful to use these lower level concepts even in the higher level languages like Python. Thank you.
Oh yeah, just hi, I'm Teo from WetFX. We dealt with that actually quite a lot. That you brought that up, it's quite interesting. The circular reference. So we use PySide. So that's basically allows us to use Qt from Python, for UI interfaces and things like that. And there was a bug in the old PySide implementation, PySide 2, whereby the exact problem that you described was happening. So we had a circular reference of two widgets that were just referencing each other, but they were not unreachable by the rest of the code. And it was inside a multi-threaded application, and the garbage collector decided to destroy those widgets from a background thread for the garbage collector, and that caused the program to crash at random places. So we tracked that down, and then just raised that with the Qt company, and they fixed it. So now they're making sure that the garbage collection of their Q widgets only happen on the main UI thread. So that's just a note on that circular reference. This causes real problems if it runs in the background thread, especially uncontrolled in that fashion. But the Qt company fixed it, so PySide 6 is all good.
That's an interesting story to hear. Threads always cause problems like that, especially.
The problem is the garbage collector can run at any point in your program, implicitly on any thread. So then Q widgets obviously not being thread safe and can only be destroyed in the main thread, thus causing the crash, but at random times and are completely unrelated. So it's very hard to diagnose because randomly crashes. You don't know why. It's just the garbage collector triggering it.
So for those exact examples, which he showed that are actually in the real world. You can use manual intervention like this. You can even create automated things that like basically based off of conditions, start the garbage collector, stop it. I was writing a program for that, but I couldn't finish it beforehand, so I just decided not to show it. But you can definitely do that, and it will be useful. So yeah, learn about the Python garbage collector.
You can make your program crash.
Yeah. Any other questions? Oh yeah.
Question: Python, when it allocates the heap, it does it in large chunks, doesn't it? Like when it's run out of heap, it takes another large page, and even when you garbage collect that entire page, it won't release that page. And so I've noticed in long-running Python processes that allocate a lot of memory, then release a lot of memory over a long period of time, that Python, on the outside, the Python process never lets go of that memory. But internally, it continues to reallocate the heap into the pages that it's already claimed from the operating system. Do you know if there's a way of telling it to stop doing that? Or do you know about that?
I don't know about any Python specific things, but I do know about that you can import C types in Python to do that. Basically, how I would do it would literally just be using the C types library and then doing it the C way. But I don't actually know any specific Pythonic way of doing it.
There's one in the garbage collector library. The GC library itself actually has a function called get referrers. So that's builds on that the ref count that you described from the sys. But what I'm talking about is you give it an object and you think you have no references to it, but you can actually ask the garbage collection, tell me all the objects that are referencing this object that I now have, right? Even if you think that you don't reference it anywhere anymore, and it comes back with this massive list of closures and lambdas and just random things that you didn't even know that your object is still held by those things, these closures and lambdas specifically. I mean, that's what we encountered. And then you can start traversing it and backtrack, that's allocated there, or that comes from there. And then once you truly know that's gone, and that comes back to what you said, you actually know that this is gone now,
Can you?
Yeah.
I do know about that, but can you actually deallocate the, I guess, the memory chunks with that? Or
No, it basically just tells you where you're holding it.
Yeah.
Yeah, so you look
I've
at your
done all
source
that. I mean, there's a thing in the GC thing that tells you how much heap it's allocated but hasn't used. And the problem that I've had in the past is that you allocate a whole lot, it claims 10 gigs of memory, and then you throw all that stuff away and it's telling you I've got 10 gigs of heap memory free. And it's like, great, but are you going to let go of that? No. It's fragmented other things through those heap pages and it won't come back.
I mean, on the process list, I would look at the virtual memory versus the resident set size. The virtual memory is irrelevant, but the resident set size should go down. So if that's not going down,
it doesn't.
then
That's the specific problem.
then just look towards the garbage collector or what he mentioned. Then there's environment variables that you can set for malloc debugs. So basically, it tells you when it calls malloc and free, basically on the C level. That's what Tane mentioned as well. So you can do that as well, and it just prints out when it does the actual heap allocation and free.
Right.
Okay.
Not to use so much memory.
Yep. Any other questions?
So I was interested, so you showed this example with the list, right? Like A equals list. But could you have done that with just A equals 4? Like everything in Python is an object, right? Does it still work if you just say A equals 4? Is the 4 on the heap and the reference to it on the stack? Is that conceptually what happens, or?
I'm pretty sure. Yeah.
I think it depends on the Python interpreted version, but I think it stores the numbers.
There's a
between,
trick.
There's a trick. It has a list.
Pre-allocates 100.
Yeah, exactly.
Yeah.
They're fixed in one place.
In theory,
Yeah. So it depends on the
they
number.
always reference the same ones just as a speed optimization.
That's
It's so common.
Yeah, the ID will tell you. So if your A equals 1, it's always that same one. So ID will tell you.
Right.
1 is actually reserved. Yeah.
I thought it was a trick question.
No.
I was wondering, if let's say it wasn't a common integer, it was some random.
Try bullying.
Try 1,000, and then you find it's different than 1.
Yeah.
Like ID will tell you basically.
Great talk, Tane. Do you know any tools for memory debugging?
GC.
just like you said, just using GC and
Yeah.
printing and stuff.
Yeah,
So you
it'll-
kind of more interactive tools.
Yeah, it gives you a lot of information. Like even I stopped sharing my screen. Even even just like
Even my question is being recorded.
Yeah, the mics in the room.
Oh,
yeah, even this basic second thing, like I've used gc.getStats to get the objects that were actually collected in the it gave me the generation, the stats of the 0th generation. Like you can, as he mentioned, actually see what's in the memory chunks using the garbage collector.
Do you know if there's any like more general tool? Like this would be great for like debugging a specific case, but if there's like a more general tool for like an overview of your memory management, like some tools have like a
Oh, he wants a
application
GUI.
timeline.
Yeah.
Oh, yeah.
Name graph.
Press Malloc can output stuff.
memory model maps and so on, and that can help find more general kind of issues.
Use C.
Yeah.
Yeah.
The opposite,
Malloc
the
can
opposite
tell you
of what
all
he was
the
hoping for.
Yeah.
It's a nice GUI.
I'm sure you could find tools out there which are literally people making libraries on GitHub which are GUIs, but I don't know any, since when I want to do proper memory management, I just go to C or C++ or something like that.
The trace malloc thing that gives you a context manager in Python that will tell you the changes between
Yeah.
two contexts that you switch between.
Yeah.
So it'll say like I'm here, and you put a little break in it, and then you keep going. Trace malloc will say, well, since you last asked me, these are all the things that have gone onto the heap, and that can be very useful for figuring out where you've linked memory somewhere along the way.
Yeah.
But yeah, there's plenty of them out there if you just Google.
Yeah.
Some have GUIs.
Yeah.
But they're very hard to understand.
So I was curious in if weak referencing is a thing, and it looks like it is a package within that. It'd be interesting to run your little test again using appropriate weak referencing and see how that performs. But then my question was around like similar. You said you found a lot of memory leaks with your lambdas or closures.
Yeah.
Oh, yes.
So
Yeah.
Unexpected. So that, yeah.
So if there's like weak references in other languages, I know there's like a capture reference. So is it sort of another concept? Is like the references that get captured by a lambda? Do you know if there's a thing for that? Like an equivalent to that? Or do you somehow use that weak references library? Or the
That's getting quite deep into it. I don't actually know too much about that. I can't really answer that, but I think it's probably just the same.
just similar syntax, but
Yeah.
I don't think Python makes a distinction between I don't think it has an inherent like closure reference as like a weak reference internally. I think it just has one reference type to begin with. I'm not sure exactly how weak ref works, but I think closures don't have that kind of semantics. So
yeah.
But lambda is treated differently. It's not just the
Yeah.
syntactic sugar.
it is like
It's got namespace.
cell.
Yeah, you get the
It's
code
locked down.
object back. I mean, if you ask it, who's referring to my object, it gives you back this lambda code object. I mean, code is an object as well. And then you can figure out what file, what line. You can ask it, or you can ask the code object, where do you actually live? And then you look at the source code, and then you go, oh, it's obvious now. I know where it comes from. So it's more like a manual process. Yeah.
If anyone knows, I'd love to see just. I've never written code like that before, so I'd love to see just an example of. I mean, I can see pretty quickly how you'd use a weak reference, but the capture reference, I'll Google it later.
I would be happy to send this code out if there's any way of doing it. The 3 examples, just like give it to anybody who wants it, but I could just upload it to Git or something after this, and then you can use it and edit it for your own tests. Any other? Oh yeah.
Garbage collection itself would induce
Just a comment on
overhead,
the,
right?
on the event.
Is there like any best practices for instances like, oh, this often is should be probably doing, or too much is much overhead or something like that, especially in the industry or in making big application.
Yeah, so if it's like just a short function call, you shouldn't need to manually, I guess, manually trigger garbage collection yourself. But when you have longer processes, or like you're doing something like me where you just append as many things into a list as possible, it probably is best to intervene. It's just that the garbage collector, so if we were to run the program, if the program didn't need garbage collection at all, if we just stop the garbage collector, the program that doesn't have a garbage collector will be faster. So basically, unless there's an excessive amount of data being created in a short amount of time or something like that, don't intervene with Python's good garbage collection.
If you have time-sensitive code where you've got a good place to stop and do garbage collection, you can do that.
Yeah.
So you can go through a loop and do a bunch of work that you know is going to use a lot of memory, but you need it to finish in a finite amount of time.
Yeah.
And then garbage collect when you're not busy.
Yeah, that too, because garbage collection does make the amount of time the program runs for like not actually predictable, since it can collect at random times depending on how you run your program, when you run your program, and such.
But yeah, if you do that, if you turn it off, always use try finally. Never without try finally, because otherwise the exception comes along and you never turn it back on again.
Yeah.
And then your program just
I think there's a context manager to turn off garbage collection for a block, which is a good way of doing it.
yeah, context
Reminds
manager.
me- Reminds me of PostgreSQL or database constraints in general. When you want to get a lot of data in, and you know I'm going to fill this table and this table,
Defer
this
all the
table,
constraints.
yeah, and just disable all the constraints and then bring them back when you're done can be so much faster. But it's a dangerous business, isn't it?
You mentioned that the reference counting isn't thread safe in Python. Is that a Python specific thing, or
Yeah,
do you know that it
basically.
works in other languages that are multi-thread?
Well, I guess the main thing is that it can cause race conditions like he was talking about, which race conditions are in every language, but this reference counting thing specifically, like the reference counting affecting it specifically, is Python.
And usually the guild takes care of that for you, you know. I mean, this was the Q widgets because they're implemented in C++,
Yeah.
and there was the underlying problem. But usually the guild, you know, like if you're using a Python dict, you know, from 2 threads, it won't crash, you know, that's, you know, but their data structures like a collections.dic, you know, that are blended Q, they are guaranteed to be fully thread safe. Or you can use threading.q or something like that. They have locks explicitly around them as well. Right? Yeah. So there are locks as well, you know, for that kind of stuff.
And does anybody else have questions? Okay.